In this video, we're going to look at a more general form of expanding a binomial. So rather than specifically look at binomials of the form 1 plus x, we're now introducing the option of the binomial having a pronumeral other than, or a number other than 1 in this spot. We're just basically looking for the pattern that develops, and we'll use that pattern then and apply it in any situation where a binomial is raised to a power. So you know that in a plus x to the naught, then anything raised to the 0 power is 1. It's not really telling us very much. Let's have a look at the next situation, a plus x to the 1. We'd normally just write that as a plus x. Now, because we're trying to make connections to Pascal's triangle to identify coefficients and what is actually happening to each term in the binomial, that is the a in this case and the x, then I've broken it up more into this format. So you can see the numbers of Pascal's triangle turning up there. You can see that a must have been to the power 1, x was to the power 0 because there was no x term here. Then a goes to the power 0, x to the power 1. We're really going to be focusing on what the indices are doing if they're and just identifying the pattern. So moving on to a plus x all squared, you can see that we would normally just say square the first, twice the product of the two, square the last. But breaking that up, we can see that the coefficients are following Pascal's triangle. A squared, so the first component of the binomial, has the same power as the power the binomial was raised to, and x is to 0. So maximum power, 0 power. Next term, got the coefficient according to Pascal's triangle. The a is coming down in power, x is going up in power. Third term, again, the coefficient is that of Pascal's triangle, and the index of a continues to come down and the index of x continues to go up. So that basically is the pattern. We keep the coefficients according to Pascal's triangle, and we take our first component of the binomial and give it maximum index, and the second component 0. So then the first component's indices go 3, 2, 1, 0, and the second components build up from 0 to 1 to 2 to 3. So basically, like I said, that's the pattern. There are many similarities. With 1 plus x to the n, you'll see it has the same coefficient. There are n plus 1 terms. The powers of a decrease as the powers of x increase, and the sum of the powers will always be n. It's possible to use the notation, the NCR notation, which is defined as n factorial on n minus r factorial, providing we accept that the 0 factorial is 1, which you can see by the little proof there that that is the case. That then allows us to work through to a very general expression for a binomial expansion, where we've got a plus x to the n is coefficient nc0, which is 1, a to the maximum power x to 0, then nc1, which is really the second coefficient. So we just have to get used to this sort of starting counting from 0, and that being our first term. Second term, come down 1 in power for a and increase the power for x, and continue along for as far as we can go. The first and last coefficients are NC0 and NC1, and they're always equal to 1, and we'll show the proof of that later. There are always n plus 1 terms. The second coefficient belongs to the second term, which has x to the power 1. So this is the second coefficient. This is the second term, however x is to the power 1. That pattern continues. The second coefficient can be written in the form NC1, third coefficient, and so on. And the reason that we're pointing this out and emphasising it is because there are many questions that talk about finding the coefficients, equating coefficients, or finding the greatest coefficient in an expansion. Coefficients follow a symmetrical pattern. The middle coefficient will be the largest coefficient. And again, you might wonder why so much emphasis on coefficients, because many of the questions require a good understanding of what's happening with coefficients. And in terms of the middle coefficient, if n is an even number, then there are an odd number of terms. If there's an odd number of terms, there's just one middle term, and it will be this n on 2 plus 1. You can trial that with some simple numbers. When n is odd, then there are two middle terms, and they will be the n plus 1 divided by 2, or the next one along. Each row is reversible. We'll do lots more work on that. The sum of each row is 2 to the n, and each coefficient is the sum of the coefficients from the line directly above. I'll do the proofs in another video.